Okay, so we are looking at the law of sines. We just did an example with it. And now we're looking at the weird case. This is the case that a lot of people struggle with. It's very abstract. It's kind of weird to get a hold on. Hopefully we should have a good example in class to help illustrate this, but I'm going to come up with a slightly different one. So we're talking about a triangle where we're given two sides and an angle. And they're very careful to always write this SSA. And I remember this because in geometry, if you flip the letters, ASS is a bad word. They don't want to put that in high school textbooks. So the ass triangle is the weird one. So I have my angle alpha. And in all of these triangles, they put alpha here on the bottom left. Then I have two known sides. A, which has to go opposite alpha because of our triangle correspondence. And it shows up twice there. And B is this side that comes off of our given angle. And then our third side is, it's kind of like we have the ground and we don't know how far along this straight line we're going to measure. So one of the ways I've described this is like having a crane that's trying to hang some sort of fixed length things. It kind of falls apart, but all right. Let me try a slightly different one. Let's say we have two lengths of pipe. They're already been cut, B and A. And I know I have to put B at a particular angle to the ground. So like I fix B in position, that's stuck. Now I've got my A, and where A goes is now the question. So the first one is A even big enough to hit the ground to make a triangle? So we can actually have a setup of case A here where side A is too small. Now the H they're talking about is right here on case B. If I made this a 90-degree angle, then this A length here is the minimum I need to actually hit the ground off my first pipe. Now to figure out the length of that, because this is really the H they're talking about everywhere, I'm going to look at the sine of alpha. So the sine of alpha, sine is opposite A over hypotenuse, the thing across from the 90-degree angle, B. And then if I get A by itself by multiplying by B, then I have that A is B times the sine of alpha. Or really, I should call this H. So if A is at least this length, B times the sine of alpha, then I can make a triangle. If A is smaller than that length, then I don't even get a triangle. It's just with the angle where it is and the side length going out so far, there is a minimum length A can be in order to connect all the lines. So there's our minimum, but then it's a, well, is there a maximum? Like, what's going to happen? So if I make A super ridiculously huge, which in this case is really just bigger than B, then I get just one fixed triangle that's going to be really wide. Because think of A like being 100. It'll make a triangle. look weird, but it'll make a triangle. Or if A equals B, then those two sides are equal, which is about how the picture looks. But if I tried to bring the A back over to the B, they'd line up, it wouldn't make a triangle. So the case we're really going to focus on is this ugly mess. This is the weird case, where our A is big enough to make a triangle, bigger than that height, but not as long as B. All right? So I've got my two fixed lengths and that guaranteed angle that I put the one length of pipe at. Okay, so here they've thrown together this potential triangle. What we're going to check first is, can this even make a triangle? So our minimum height is B times the sine of alpha. So B is 8. And then alpha is 35 degrees. Pull out the handy dandy phone calculator. Sideways. Yes, I'm in degrees. 8 times the sine of 35. All right. So we get H is 4.588, blah, blah, blah. So that's our minimum needed to make a triangle. 6 is bigger than that, so this definitely makes a triangle. 6 is smaller than 8, so this makes 2 triangles. All right, so let me type that. So since we can make 2 triangles, let's go ahead and draw the figure with both triangles. From the way it went last semester, I think seeing the full crazy figure will be better than trying to figure out where something moves. Okay, so there is our ground line, if you will. And there's our B of 8. This is our alpha of 35 degrees. And then this 6 can go one of 2 ways. So remember, these are fixed lengths, so I can't make them longer or shorter. So it is one of those two. Either it swings in close to the pipe or it swings out further away from the pipe. But if I try to stop it in the middle, like the pipe would be trying to dig into the ground. Or I'd get some weird 3-dimensional figure that we don't want to figure out. Now, wherever I swing this pipe, even in 3 dimensions, there is an angle here. That one there. And it turns out that angle is actually equal to this angle here. So that length of pipe, regardless of where I drag it, as long as it's attached to the end of B, this particular angle is constant. So we need to figure out what that angle is. Now remember, our A here is 6. So in either case, that's 6. But that's going to be our beta. And then we're going to have up here, that will be our gamma to go with our regular beta. And then this huge long thing will be C. So that is the first triangle that we're going to use the law of sines to calculate and figure out. All right, so let's set it up. I've got 35 degrees and 6 is my given pair of corresponding side and angle. And I have b equals 8. So we're going to do alphas and betas, a's and b's. So the sine of alpha over a is the, oh, let me use my colors, is the same as the sine of beta over b. Let's go ahead and fill in our known quantities. Sine of alpha is sine of 35 degrees. A is 6. Sine beta is the thing I'm going to solve for. And that corresponds with 8 for side B. So in order to solve for the angle here, we're going to have to use an inverse trig function. But I'm trying to get beta by itself, so sine of beta by itself, so I'm going to multiply by 8 on both sides. Now bear with me, I'm also going to flip the equation. Nah, I won't. All right. So we have 8 times the sine of 35 over 6. This is equal to, and I'm going to leave a little space here and write the sine of beta. Now, if looking at this, you're seeing like we say sine of beta, so that means sine times beta. It doesn't. Unfortunately, in math, we use the word of in 2 different contexts. When we're just like describing a thing in English words, we'll use of to mean multiplication. But now we're studying functions and how functions work and how to undo functions. Function notation gets read f of x or sine of beta. But that of is not multiplication here, it's applying a process. So to undo taking the sine of beta, we have to do the undo function for sine, which is inverse sine. And just like with the square root, we apply it to the whole sides outside. So it's going to be the same thing over here. I have to apply sine inverse to the whole thing. And there's not a pretty way to like distribute the sine inverse here. It doesn't work like that. Like it's pretty much impossible to break something inside a trig function outside of it without doing some really crazy math that makes everything worse instead of nicer. All right, so we need to calculate that mess. So I'm going to start with sine inverse, and then that opens a parenthesis, 8 times the sine of 35, which open a parenthesis, so I close that, divided by 6. And then I close that. So this tells me that beta is 49.8864, blah, blah, blah. All right, so when I look at my weird figure here, that green beta I drew in is, just go ahead and call that 49.9. So beta equals 49.9. So I have 2 of my 3 angles in the large outer triangle. Like, let me give that a kind of Like that's the triangle, that's the angle it gave us, is this beta here. It's the same as this little angle here, but it doesn't correspond to this large leftover angle here. Like in the middle of that flat side. All right, so if I know this angle is 49.9 degrees, I can find gamma because all three angles add to 180. So alpha plus beta plus gamma is 180. So we have 35 plus 49.9 plus gamma is 180. One sec. Me and my giant handwriting, I need more room. All right, so that is 84.9 plus gamma is 180. So gamma is 95.1. All right, so bring it back up here. That big angle is 95.1 degrees. I can use that now with my law of sines to find the big side, side C. Okay. So I know in my law of sines, I'm going to have sine of gamma and C, because I'm solving for C. So I can either put my alphas or my betas. I will choose the alphas because 35 and 6 were both starting values. That way I'm not trying to plug in 49.9 because then it kind of begs the question, well, how many decimals should you carry? I'll just take the 35 and the 6. I don't have to worry about it. All right, so let's fill in our nodes. This is that same sine 35 over 6 that we used before. But now it's equal to the sine of, we know gamma, 95.1 over C. All right. So we want to get C by itself. So it's one fraction equal another fraction. You can cross multiply, divide by the third, which is what I just start shortcutting to after a while. So like looking at this, my brain says, oh, this is going to be 6 times the sine of 95.1 divided by the thing that's across from C, the sine of 35. I'm going to show you why that's true, that is what C will equal. So if I multiply by my common denominator, 6C, 6C, I get C times the sine of 35 equals 6 times the sine of 95.1. And then I just divide by the sine of 35 on both sides. And there is what C equals, and now we can actually crunch that up in the calculator. So watch out for your parentheses when you do this. The calculator is going to open one for the angle. You need to make sure to close it. It'll open one down here, close it. And since it's multiplication on top, we don't need another set of parentheses, but if you just want to be extra sure your calculator is doing what you want it to, you can put another set around everything on top and even another set around everything on the bottom. The calculator should work without doing that, but that's like if I have the world's dumbest calculator, this will guarantee it works. So 6 times the sine of 35, nope, 95.1, close and close, divided by open, the sine of it opened, 35, close, close. So this tells me that C is 10.419, blah, blah, blah. So that is 10.4. All right, so if I take my 6 measure pipe, swing it towards the outside, I'd have to have a 10.4 measure pipe to connect the sides. All right, but what if I don't have a pipe that long, but I still need to weld these things together to make some sort of triangle? Then we have this inner weird triangle. So that's what we're going to figure out the measures for now. So let me see if I can't pull some of those measures for y'all, like just to. All right. So again, this is our 35 alpha. B is 8. And then down here, these two guys are 49.9 degrees. So the triangle I'm focusing on now is this little one on the left. So I have to keep my 35 degrees as A. That's given, it's fixed. I can't move the angle B is sticking out at. But I can wiggle side A so it's closer in. So this is still the side opposite alpha. So that is A equals 6. But this angle we found before, remember this pipe makes an angle with the ground that's the same regardless of where I drag it around. So if I line it back up here so it's in line with B, so I can make this distance as close as possible, I want to figure out that now obtuse angle. So since I know 49.9 is this one here, then this purple one I labeled is across from B, so it is technically beta, but we don't want to call it just beta because then it gets confusing with the first triangle we drew. So what the book usually does in this case is they call it beta and then they put a prime, which if you take in calculus, this has absolutely nothing to do with derivatives. It's just we haven't used primes yet in pre-cal, so sure. It's one of the ways to mark extra alternative things. That beta, the measure is going to be 180 degrees minus the beta we got in our big triangle. So we're going to find this new beta prime. Once we have the new beta prime, we can find our new up here. Remember, this is gamma. So this skinnier angle here is going to be gamma prime. And then we can use gamma prime to find our smaller C side. So I know a whole lot of work to figure out, all right, well, how much pipe do I need since I don't have the 10 feet or whatever? But we can do it. All right, so it's still going to start the same. We're still going to have the same sine alpha and sine beta. But over here now, we're going to have apologies. We actually have beta prime, like we can just calculate it because we have beta from the first part. All right, so 180 minus 49.9 is 130.1. Now to find gamma prime, this isn't 180 minus gamma. Like if you look, first gamma was kind of big, this one is going to be smaller. But we get this gamma prime from alpha and beta prime. So gamma prime is 180 minus alpha and minus beta prime. So 180 minus 35 and minus that 130.1 we just calculated. We get 14.9 degrees. So now that I have gamma prime, now I can use my law of sines to find what should be labeled as C prime. So sine of alpha over A. And this is the other reason why I prefer to use the given one is this ratio is the same regardless of which triangle you're trying to figure out. And then sine of, we know our gamma prime. I'm trying to find C prime. Now, if instead of using the C prime, you just want to call it another letter, same with the beta prime and gamma prime. If you just want to call them other letters, that's fine. Just make sure you label it so you remember what was what. Sine of 35 and 6 equals the sine of the very small 14.9 over C prime. All right, so C prime is across from the sine 35, so we would eventually divide by that. So we have to multiply the other two things. So C prime is going to be 6 times the sine of 14.9 divided by the sine of 35. Six times the sine of 14.9 divided by the sine of 35. And it's telling us that this little small side is 2.6897 blah, blah, blah. So like 2.7 inches or feet or whatever. So in the big triangle, it was 10.4. In the little triangle, it's only 2.7. So even if I couldn't make the big triangle, if I still have 2.7 feet, I could still make my wonky, more slanty triangle. Okay. So I know all of that work, all of that insanity for one problem. All right, cut this and start the next one.